So, hello again. I kind of messed up. I didn't realize there were a couple more slides left, so I'll just do a quick little video and wrap it up. So, we finished the story of stars, or at least most stars. Most stars go through this cycle right here. They're born from a nebula of material for a long, long time. The vast majority of their life, they sort of burn hydrogen into helium on the main sequence. Then eventually they swell up into a red giant and a red supergiant as their core starts to shrink and get hotter. And for a brief time, as you can see, they become what's called a planetary nebula, where the outer shell drifts away and it's lit up like a lampshade by this inner core of very hot, white hot carbon. And then that ball of carbon is called a white dwarf. And for billions of years, it will just sit there in space and eventually cool off into what we call black dwarf. And that's where we left off. But there were a couple more paragraphs here in your notes. I apologize. What about those really big, massive stars? Well, listen, that's the next chapter. So I'm not doing this, this is just a very, very short summary just to introduce that. What about the big stars? Well, they're not going to last long on that main sequence. Heavier stars burn out faster. Okay. They have a really short lifespan. They burn out their fuel very, very quickly, and they're going to swell up. And look at the difference here. So I don't know if you remember the spectral types, okay? O, B, A, F, G, K, M, from the hottest stars to the coolest ones. Our sun is a type G, for example, so we're on the cool side, and our sun will burn on the main sequence for 10 billion years. But you get up to a type B star like Spica. Type B stars, look at that. They only burn for 100 million years. That's not much time in terms of a star's sort of lifetime, right? Compare that to 10 billion years. That's 1/10 of a billion years. All right. So they burn out 100 times sooner than a star like our sun. That's type B. Of course, everybody wants to know about type O stars, the hottest. They might only burn for 20 million years. That's a blink of an eye in cosmic terms. That's really fast. These stars are born and poof, they're going to blow up pretty quickly. So in this case, they do swell up for a short time. And one difference on an HR diagram, the way they evolve is a little bit different because they're already super bright. See, a star like the sun, when it swells up eventually into a red giant, it will get much, much brighter. But these stars were already super bright. So on an HR diagram, they stay at the same very high level of brightness on an HR diagram. That's what I mean by that. When I say they move horizontally, just means that they change. Their brightness isn't going to change. Okay, they're going to stay the same level of brightness. The temperature is going to change and the size is going to change, but not that. And at this point is when you can start fusing heavier elements. Because let's face it, we only talked about elements up to carbon. Carbon's number 6. I mentioned that little stars maybe create a little bit of oxygen and neon and stuff like that, but that's not getting you very far down the periodic table. How are those heavier elements created? Well, these are the stars that are going to create them, only the big massive stars. So they're able to create in their super hot core even heavier elements. We'll get into that a lot in the next chapter. And of course, everybody loves the big massive stars because they may blow up. And if they're above a certain level, they are going to blow up. So let's take a look at those sort of levels. So for example, a star like Rigel in Betelgeuse, it is what we call a blue giant, 17 times heavier than the sun. It's going to blow up. That is its fate eventually. And of course, more famously, its sort of partner in the beautiful Orion Constellation is Betelgeuse. And there's a lot of speculation at the moment right now that Betelgeuse may have already blown up. It's possible, at least. It's possible. But Betelgeuse, that's its fate as well, is to blow up if it hasn't already. So, anyway, what are these magic cutoff lines? Well, here's the deal. We're going to define, roughly speaking, 8 solar masses is the key. 8. The number 8. Remember that, okay? What am I doing here? It looked weird because it's reversed mirrored on the screen. Sorry. Yeah, 8 solar masses. 8 solar masses. When that star is born, if it's below 8, it's going to be safe, unless it's in like a close binary, and But if it's born just kind of on its own, a star like our sun will never ever blow up. I I hear people say that all the time. Hey, when's the sun going to blow up? The answer is never. The sun doesn't blow up. Stars like the sun don't blow up. But if it's born above 8, there's a very good chance it'll blow up. If it's born above 12 solar masses, it is going to blow up. I mean, that's its fate. That's it. So, and again, there are some weird exceptions when you're in a close binary and stuff like that. But for the most part, that's the deal. Now, what about this 8 to 12 business? Well, if you're born, let's say, at 9 solar masses, at the very end of that star's life, as it's swelling up and shrinking down and swelling up and shrinking down, and it's very unstable, which I think is where Betelgeuse is at right now, it actually starts losing material. It loses weight. It throws out material. And so it could actually dip below the magic number of 8. You know, if it starts at 9, but it throws out 1.5 solar masses of material, maybe at the very, very end, it dips down to a 7.5 and it never does blow up. So stars can sort of save themselves possibly at the very, very end, they think. But remember, above 12, you're a goner. And look at Rigel. I mean, Rigel's, you know, it's going to blow up for sure. And if you're wondering where these beautiful stars are located, just a refresher, here is Orion Constellation, Orion the Hunter. There's the famous belt. There's Orion's sword. That's what we look at astronomy night, the Orion Nebula right there. And then look at this. Below the belt, you have Rigel right there, the seventh brightest star in the night sky. And then above the belt, Betelgeuse, which is normally almost the same brightness. It's the 9th brightest star, but over the last year, its brightness has dimmed mysteriously. So that's kind of cool. All right, folks, I think we're now finally caught up. I apologize. Yeah, so this is on a separate video. And so make sure you watch all the videos and learn a little something, okay? Thanks for watching.